Welcome everybody. My name is Antonio, and I will present something about myself a bit later. We are here for, as Liliana explained, for this workshop on explainability in artificial intelligence for the specific field of climate modeling, in which we are going to talk about the impact assessment and the decision support that these kind of techniques have for the users that use this kind of algorithms. Before going on, I would like to do a Mentimeter in order to just know something more about you. I will share the screen. I think that you can read the QR code or just go to Mentimeter. I will copy the link on the chat, and you can just place the code. The code, which is 39611057. I will copy the code also in the chat. Here is the code, and I will share the screen of the Mentimeter. Okay, Serbia, Italy. I don't know if you all have access to. Yeah, I see that there are 12 participants, so almost all of you responded. Reading UK, right? Spain. So great. I think that from almost every country that participates in the consortium. Okay, we can go to the next question, which is just to know if there's somebody from outside the consortium in the workshop. So for now, everybody from the consortium. I see that there are people joining right now. We're 17 in the Mentimeter. Okay. So there's somebody from outside the consortium. Great. So I think that we can go to the next question. Just to know in which background you are. I will explain mine later on the presentation. So there are many people from the other. We can discuss where you're from then in the event discussion at the end of the workshop. But well, 25% of computer science engineering. This is because at the end of the workshop, the last part will be a hands-on, which is like with coding and all this stuff, which might be better for this kind of people. But all are, I think that all of you are gonna enjoy it. Great. So we can go to the next one. How familiar are you with machine learning? Well, I don't even consider myself as advanced user, but well, I have say as advanced if you have ever built a model or train a model. Great. So at least everybody considers as a beginner. So you might have like the basic concepts. Great. Great. And this is just an open question in which I would like you to think about the last time you questioned a prediction made by an AI model. As an example, I could say the last time Netflix suggested me a movie, for instance. Like the last time the algorithm of Netflix suggested me a terror movie, and I don't really like terror movies at all. So think about just one time in which AI said something and you didn't consider it right. It can also be like a recommendation in the shop list or whatever. Yeah, that's right. Also, the Instagram algorithm. Great. Twitter timeline. That's true. Yeah, I think that the Instagram advertising is a difficult one. I don't agree with it many times. Also, that like when you are in the Explorer, they recommend like short videos, and many of them are related to topics that you are not interested at all. Great, great. Yeah, I think that recommendations for shopping ones. Yeah, yeah. That's very annoying. Almost when you are talking with a friend about something you want to buy, and then in the websites there that you are visiting, you start watching all the time advertising about that product. That's annoying. Okay, so I think that we can go to the next one. The next one, I think that they are going to be like a little quiz. Don't feel bad if you select the wrong answer. Yeah, that happens a lot. Uh, um, don't feel bad if you get the wrong answer, because they are going to be answered during the lecture. So the hope is that at the end of the workshop you will know the right answer. So what does interpretability mean in machine learning? The ability of a model to self-correct, the ability for a human to understand why a model made a decision, and the accuracy of the model on unseen data. Well, almost everyone is going for the second one. And I have to say that it is the right one. So we can go to the next one. Somebody said the ability of a model to self-correct. That would be like that would be like the algorithm with the back propagation algorithm, that is the one that keeps calculating the weights of the model to adjust to the data. And the accuracy of the model on unseen data, that's not interpretability, that's just like accuracy. But it's great. So now, which of these algorithms is most interpretable by design? Like, which one do you think that you can get interpretable results just by the results of the algorithm? So nobody chose random forest. The decision is between linear regression and neural network, it seems. And many of you chose linear regression. We will answer this question during the lecture, but a neural network would be what we consider as non-interpretable, as a black box model. And now, where would you fit these models? We are saying like this is like 4 coordinates. To the left, we see if you locate the number to the left, it will be more simple. If you locate it to the right, it will be more complex computationally. And the y-axis is just in the bottom. The model lacks of interpretation, so it is not interpretable at all. And in the top side, you are considering the model as explainable. Okay. Yeah. For now, the responses are in the path of the correct answer. I don't know if you are seeing the responses in the mobile app or in the desktop. I mean, you can see my screen, right?
Yes, we can see the screen.
Okay. Yeah. So the neural network would be the more complex one. That's right. And the one with more lack of interpretation. And the random forest would follow. Not the decision tree, but the random forest, which is an ensemble of decision trees. And then the decision tree would be like simpler than the random forest and more interpretable. And also the linear regression is just the simplest one and the more and the most interpretable or explainable. So you are almost right. Well, the decision tree you said somebody said that lacked of interpretation. We'll see an example later about this. Well, almost everybody locates the linear regression on the simplest one, and the neural network go to the complex side. Yeah, that's great. So now, what words or adjectives come to mind when you hear that a model is a black box? What do you think about a black box model in artificial intelligence? Scary. Uninterpretable. Unexplainable. Not public. Not understandable. It does its own thing. Close. It does what it wants. Unfair. Unknown. Risky. That's a nice one. And this is something that would think like a person who has been working with climate data as we are in the project and traditional algorithms during his life or her life. They would say that machine learning algorithms, which are what we consider black box, especially deep learning algorithms, because you know what is going inside the model, you know what is going out of the model, but you don't know what kind of interactions are happening exactly inside the model. You have a set of neurons as it would be a brain or a human brain. You are trying to replicate the structure of a human brain joining neurons, but you don't know the interactions between the different neurons in the different layers of that brain. So that's why it is considered a black box. You know what is going in, you know what is going out, but you don't know what's happening in the middle. And this is why many people consider it as risky. So that's a great one. Well, I have just responded this one, I think. So the second one is not going to be. If you take my words just 1 minute ago, the second one is not going to be. So yeah, these black models need like a set of techniques to use after training to interpret the results and their predictions. That's everyone chose that one, so it's great. Okay, so what do you think? Which one of this you think is a real world problem caused by poor interpretability? Slower turning times, misleading or biased decisions that can't be easily explained, or less storage space? That one was this one was an easy one, I think. So yeah, everybody chose the middle one. So no much comment. Yeah, the interpretability techniques do not affect the training times because it is usually done after training, and the storage space is not affected by the use of interpretability techniques because you are using the model that you have saved during the training process. So it was the second one, which is like poor interpretability uh, can cause misleading or biased decisions because you are uh, putting faith in a prediction of a black box model, which you don't know how you got. And I think this is the last one. What do you think a saliency map is typically used for? This is like an advanced one. So visualizing which input areas most influence the model's prediction, monitoring model performance over time, or highlighting neuron activity during model training. I think you are all going for the first one, which is the correct one, and I will explain later what is a saliency map, and I will give some examples about them. So I think that was all. Yep, that was all. So I'm gonna start. I'm gonna stop sharing and going back to the presentation. Got it. Right. So can you see the slides?
Yes, we can.
Okay. So just well, you have said some things about important stuff about you. Just that makes me know better which kind of audience I have. I think that all of you are gonna enjoy the presentation and at least some of the hands-on training. So myself, I'm a data scientist at Predictia institution. Many of you already know me from the ClearClimate project, and I am working on the intersection of artificial intelligence and climate science. I especially have expertise in the generation of data pipelines to um, communicate the data with the modelization part, and I have also expertise in that modelization. I use artificial intelligence for weather and climate related problems, and I have also used explainability techniques applied to the models that I have produced in the previous part of the whole pipeline of generating data, training a model, and explaining the results. I have a Bachelor of Science in Physics, a Master of Science in Data Science, and now I'm doing a PhD in collaboration between Predictia and the University of Cantabria. And my research is mainly related with the work done in Work Package 3 of the ClearClimate project, in which I am trying to generate AI-driven high-resolution regional climate projections using downscaling approaches with reanalysis data and with the global climate models. Well, my work in Work Package 3 is basically related with this. I'm trying to generate regional projections using AI. I am taking two kinds of reanalysis, one at low resolution, which is ERA 5. It is like 25-kilometer resolution, and other in high resolution, which is a European reanalysis at 5.5-kilometer resolution. So there's a difference of 5 times the resolution between one another, from 5 to 25 kilometers. And we are trying to extrapolate the model trained on this data to use it in global climate projections of the same resolution. So we think that we can extrapolate the algorithm trained with reanalysis data to climate projections. We have published already a paper on this on the use of super resolution techniques to downscale temperature data of these two reanalysis data sets. You can have access of it in that. I can send you the link in the open discussion if somebody is interested. This was already explained by Biljana, but the first part of the workshop is going to be like just an explanation of what explainability and interpretability is, what kind of methods do exist, and some methods applied in climate science. And after the coffee break, I will talk. I will perform a hands-on training with some material that I have prepared on GitHub to run like real Python code on real reanalysis data over the Southeast Europe region. After that, we'll have an open discussion in which I guess there will be questions, at least about the results presented in the hands-on training. Okay, for the first part, as I explained, I will give an introduction with an analogy that I think that it's great for understanding why interpretability is important. Then I will explain the concepts of artificial intelligence, machine learning, and deep learning, which are like highly related. And then I will give a simple example of these artificial intelligence techniques, which is like the linear regression, which is the simplest one, as I said in the Mentimeter. Then I will explain the concepts of interpretability and explainability. I will say why it matters, and we'll do an overview of methods. I will try not to be too technical. I will try to be like briefer in this part, explaining like the kind of models that we can use, and the kind of interpretability algorithms that are associated to each one. We'll talk about the transparent models, which are the ones that are inherently interpretable, like the linear regression. And we'll talk about the models that need to be explained after training. Then we will talk about the limitations of explainability in artificial intelligence, and I will give several case studies. One case study based on image recognition, which is out of the climate science field, and then I will give several examples on the climate science field that I think that could be interesting for all of us, but all of them are associated to the topic of the work package 3, which is like downscaling and regional climate emulators. Right. So I want to start the session not with AI, but with a horse. In the early 20th century, like this photo is taken from 1904. A horse named Clever Hans amazed like the people from a city by solving math problems. His owner would ask him an arithmetic question like how much is 2 plus 5, which we all know that is 7, and the horse would tap his hoof the number of times which correspond to the to the to the solution. So he would tap his hoof to the ground 7 times. People were amazed by this horse, and they were like, "Okay, how can a horse do arithmetic?" But later investigations revealed something more interesting than animal intelligence. Hans, the horse, wasn't doing arithmetic or mathematical operations, in fact, but he was reading the body language of the owner. When he started tapping the hoof, he waited for the owner to do some kind of gesture to stop tapping. So yes, clever Hans was clever, but not in the way that people thought. The moral of the story is simple. Impressive answers don't always mean real understanding. And in machine learning, we have these moments as well. We have models that seem to perform brilliantly until we look under the hood. For example, I'm giving here 3 examples of impressive answers that don't mean the model is really understanding what is going on. So we have a classifier trained to tell whether the animal that is in a photo is a wolf or a dog, and it turned out that it was getting really good results, but he learned to detect snow, not wolves. So if you place a photo of a snowy area without a wolf in it, the algorithm would say that there is a wolf there, uh, even if there is no one. Also, we have an audio model trained to detect whales, and which actually relied on file metadata, not sounds. Like he relied on metadata like the file name, the characteristics of the input sound, whatever text input data, text metadata exists for that file. And also we have an image classifier that instead of learning image features, it learned like the text overlays. All of these models had greatest accuracy. They looked like they were working, but they didn't understand anything. and this is the key point. This is the key point. Accuracy alone is not enough. A model might be right for the wrong reasons. That's the key point from here. And if we are going to use these models in science and in very important fields like medicine, climate prediction, or policy, we need to know not just what they predict, but why. And that's where explainability and interpretability come in. And we will explore this during today's lecture. Well, before we dive into the interpretability and explainability definitions, we are going to take a quick look to the concepts that almost everybody is talking about nowadays. This is what we mean by AI, by artificial intelligence. And with this, we refer to systems that perform tasks typically requiring human intelligence. Inside artificial intelligence, we have two different approaches, which are machine learning and deep learning. They are like highly related. Deep learning could be considered to be inside machine learning, and they are trying to learn patterns from data to make predictions. Machine learning algorithms are usually used for for tasks like fraud detection or predicting if someone will cancel a subscription to Spotify, to Netflix. They are used in many tasks in our current society. And the deep learning, as I explained before, deep learning algorithms are trying to generate the structure of the human brain on paper, just or in coding, just trying to generate a set of layers, each layer form of different neurons, and they are connecting neurons of one layer to the other layer, just to trying to do a similar structure to the human brain. Each of these levels, the more layers you use, brings more power and more capacity, but also make the model less explainable because it is more complex and it is less interpretable. That's what makes explainability so important as we go deeper and deeper and deeper in artificial intelligence with more and more and more layers. But we can take just for taking an example of a machine learning model. I think that this is the best example. This is just a linear regression. Suppose we want to predict a price of a house. One of the most basic ways to do this is just using a linear regression, saying that there is a relation between the size of the house and the price of the house. So we are here. I took the number from a web page here from Santander, which is like the average price for a square meter in Santander. And so we are saying basically that for each square meter, you are multiplying the square meter by 2,700, and you are getting the price. This is just a very simplified example. In reality, there would be many other features going on, like the number of rooms, the number of bathrooms, whether the building has an elevator, if the flat was built 50 years ago or 10 years ago. So this is very simplified. But this example is great because it helps us to illustrate something important. Linear models are easy to understand. You can clearly see how the input affects the output. Here, it is just an operation, a multiplication. That kind of transparency is what we call interpretability. And we are going to take now a moment for explaining two key concepts. The first one is interpretability, which is about whether we can understand why a model made a decision. And here are two great definitions of interpretability. In the first one, interpretability is the degree to which a human can understand the cause of a decision. And the second one says a method is interpretable if a user can correctly and efficiently predict the method's result. What this means is if as a user, I'm able to, okay, I have an input data. What output I'm going to obtain? This means that a method is interpretable. For instance, if I have like a flat 100 square meters, I know that I'm gonna obtain a price of 2,700 times 100 square meters, and I know it. So the method is interpretable. But in my case, in the case of my PhD, if I don't really know right now what is going to be out of the model with the input as I have it. And this is what makes a model non-explainable. Then explainability goes a bit further. It includes interpretability, but add additional context like tools and like tools to visualize or attribute to features the importance of the model, and that's what help us to understand how the model arrived at that decision. So explainability is stronger. Just it is like interpretability with an additional context, and both are crucial. Both together are crucial for trust and transparency, especially when AI is used in sensitive domains like medicine, where you have to predict if in image recognition there are some models that from a radiography they say if you have a tumor in the image. So in their AI systems have to be transparent and trustworthy. Well, now, why interpretability matters? Interpretability is about more than just understanding a model. It is about trust. This is why it matters so much, because we need to build trust to the human or to the user that is going to use the model. In some cases, like recommending a movie, which is a low risk setting, maybe it's okay to not fully understand the model and get the highest accuracy. But when we apply AI in high impact domains, like I said, healthcare, finance, or climate science, we can't afford to have blind predictions. We have to know what is going on there. Interpretability helps in many ways. We can debug models that are taking shortcuts, like the example I gave about the classifier that the classifier that classified an animal between a wolf and a dog, and he was taking the shortcut of the snow. He was just paying attention. He was just paying attention to the snow to say if the animal was a wolf. That's the kind of shortcuts we want to debug. Also, we can respond to unexpected behavior, and ensure the system behaves ethically and responsibly. It also plays a key role in in social acceptance. People are more likely to accept and adopt artificial intelligence systems when they understand its decisions. And for scientists, it offers a way to extract real world insights from data driven models. So, yes, accuracy is important, but without interpretability, we risk trusting a black box that we don't fully understand. So here we can see in the diagram it is very clear. We have like a real world data, and we go through a black box model that we are not able to interpret, and to be able to interpret to be able to explain the decisions of our black box model, we have to use a set of interpretability methods to then inform the humans that are training the models, or that perform as stakeholders of the model, not as the creators of the model, but as the real users of the model. And what are the goals of interpretability? We have to keep clear that interpretability is a tool and it is not a final goal. The way you use it depends on what you are trying to achieve. First, you might want to improve your model. You might want to improve your model, as it is the case of our board package 3, in which I will give you a case study at the end of the lecture. You might want to improve your model. Maybe you are trying to fix bugs, check feature importance, or just understand why it is behaving strangely in one area or other, or with some kind of photo instead of other. And interpretability can reveal if there are shortcuts like the one I explained before. And second, we often need to justify the model decisions. That could be to users, to regulators, or just anyone impacted by the automatic decision of the model. If you are taking the model that just predicts if there is a tumor in a radiography, you have to be able to justify the model prediction to the patient, to the person who you are saying, like, okay, you have a tumor, it has been detected by the artificial intelligence algorithm that we have to do this task, and we have to extract it. Okay, but the person who receives the news could ask, okay, but there is an opportunity that the model is wrong and I don't have a tumor. Why are you opening me if you haven't seen it? And this stuff. And third, we can use it to gain insights, to discover insights. Scientists and analysts want to learn from the model, not just get predictions, but understand why the model behaves the way it does, one way or other. So ultimately, your goal shape the kind of interpretability technique that you are going to use. And this is a diagram that well, let me wait for a second. This is a diagram that represents the roadmap of interpretability methods. In general, we can divide interpretability methods in two big families. First, interpretability by design. This means using a model that is inherently explainable, like the one that I mentioned, for instance, the linear regression or the decision trees. These algorithms are simple enough for us to understand from the start. We don't need to apply after training an algorithm to understand why it is taking a decision or other. We already know when we have trained the model and we have the equations or the tree or the decision tree, we are able to understand from the start. And the second family would be like the post hoc interpretability. These are tools that we apply after a model has been trained. Especially useful. These are especially useful for complex models like neural networks. Neural networks, we can consider them as black box models, and we have to apply these techniques after training. The post hoc methods are divided in model agnostic, meaning they work with any model just by analyzing inputs and outputs. We'll take a look after this slide. And the model specific, meaning we dive into the internal mechanics of a specific model type, and you have one kind of interpretability technique for each model. A convolutional neural network cannot use the same interpretability technique as a vision transformer because they are not structured the same way. And in the model agnostic, we have like local or global. We'll explore examples from all of these categories. I will try to give you an example of the by design and also an example of the post hoc. So these are the models like linear regression, decision trees are transparent by design. So they have what we call built-in transparency. There are sometimes in which these models can look, we can look at them and understand what's going on. Even you can explain the outcome to someone without a technical background, as I did before with the linear regression example, in which I just get the price of a flat or a house without any more than just the size in square meters. Of course, not all interpretable models are fully interpretable. Sometimes just part of them are not clear, and there can be some rules in decision trees or coefficients in the linear or logistic regression that do not make sense to the person in charge. These models are the strengths of these models are that they are great when you need to justifications, debugging, or domain expert approval, but they might not always offer the best performance. We are aware that with a neural network nowadays, or with artificial intelligence, with deep learning algorithms more complex, we are getting better results than with traditional approaches like linear regression or decision trees. And this is why we need first I wanted to explain just with an example of the decision trees. Yeah, right. Decision trees, what they do is just split data based on feature thresholds. They are creating a path from root to leaf, which is really easy to follow, and this is what makes them inherently interpretable. You can just trace exactly the decision by using clear if-then rules. For instance, if temperature is more than 25 degrees and humidity less than 60%, I will play tennis today. If temperature is less than 10 degrees Celsius and humidity is over 90%, I will not play tennis today. these are really explainable techniques, and you don't need anything else apart from just following the path of the leaves and roots to go to the outcome that you are expecting. Then there is another kind, as we mentioned, the post hoc, in which you have to explain the model after training. These techniques include algorithms like SHAP, partial dependence plots, or saliency maps. Some methods are model agnostic, and other methods, as I explained, are model specific. You cannot apply saliency maps to you can apply saliency maps to convolutional neural networks, but maybe you cannot apply them to temporal fusion transformers or LSTMs. They are especially specific for methods with convolutions. These methods are powerful, but they also come with some challenges. Interpretability is often only partial, and in some cases, these post hoc explanations may not be enough. But for sure, they are extremely useful because they will help you, as I mentioned before, to debug the model and to get a better expertise of what's going on inside the model. This is an example of saliency maps. Saliency maps helps us to understand which parts of an image mattered most in the outcome of a deep learning model. Here we are just giving an example of a classification of an image classification technique. We have more than 1,000 labels for this classification data set. And from the image, you only need to know what is shown in the image. It can be a dog, it can be a food, or it can be any set of animal inside that 1,000 label set. And we can see here 3 different algorithms for the saliency maps, which is like pixel-wise attributions, in which you are trying to get the pixel that provides more information to get to the output that you are expecting. So if we are expecting a dog in the classification algorithm of the first image, we can see that in the greyhound smooth graph, in the second one, almost all the color is around the dog. The result is just a visual explanation, and we have to be aware that they are not perfect. Sometimes they highlight irrelevant parts. We can see in the first image of the dog that it is highlighting something in the low part at the right, which does not correspond to the dog. As we have explained, interpretability techniques are powerful, but we also need to be aware of their limitations. First, most post hoc methods don't truly open the black box. The black box is always closed. What they do is just doing approximations, changing the value of some gradient or some operation inside the matrix of the model, and see how it changes the output. Also, some techniques work only with a certain type of models, as we explained. For example, saliency maps rely on gradient access and may not work well outside deep learning. Another issue is that different interpretability methods can give contradictory explanations for even the same prediction. We will see this in the hands-on training. And there's also a risk of over-trusting visualizations, especially when they look convincing but don't actually reflect meaningful model behavior. Also, there is this classic performance trade-off. The more we optimize for transparency, the more we may sacrifice accuracy or flexibility. The same way that a complex model, a more complex model, can get better results in accuracy and is less interpretable. If you want to do it more interpretable, you might be reducing the complexity of the model and getting worse results. Here I am showing an example where interpretability techniques are used, and well, let me just 1 second. Here I am using an example of a vision transformer called Dino V2. It's a vision transformer from Meta, which is trained without labels, and it is great at tasks like segmentation, object tracking, and so on. So it is great to in tracking objects inside an image. Well, if there is a Dino V2, it means that there was a Dino V1. So researchers from CNRS inspected its attention maps and noticed something odd. In the model, including Dino V2, attention was focused on small regions which were not associated with the real object, but with the background of the images. These were areas with little visual information. You can see here in the Dino V2G, the last one at the right, you can see that for the cat, it was not taking almost any information from the cat. We can see that there are slightly blue pixels, but most of the information was stored outside of the cat. It turns out that the model was using these pixels as information storage. This wasn't something the model was explicitly told to do. It was a clever workaround, and Dino V2 was obtaining better results than Dino V1. But it reduced the interpretability of the results because you were not using the information of the object you are tracking. You are just accumulating information in some other pixels and using that accumulated information for doing the prediction. So a simple fix. They generated a simple fix which was like really elegant. The researchers just added the special input tokens which they called registers, whose only purpose was to serve as like an space to store that extreme information. It would be places where the model could use to accumulate the global information that was accumulating before in some random pixels, but now in the registers. So these tokens replace the unintended use of background patches, and they removed, as we can see here in the image, where we say without registers and with registers. If you take attention to the Dino V2, in both cases without registers, it happened that for the bird, it was accumulating information outside of the structure of the bird. But when you go with the registers, with this simple solution, they got the attention of the model to the bird explicitly. And now I'm gonna give you some examples on climate data. I think that we are right on time, like 40 minutes. Okay, so 5 minutes more about this. I will take some water. So I'm gonna give you an example of on the use of saliency maps in evaluating regional climate emulators. This is a work done by some colleagues at the University of Cantabria, with whom we work in a lot of projects, and they are researching in several aspects similar to us. Their objective was to study how deep learning emulators use predictor variables to estimate regional temperature. It is similar to our problem, but instead of using temperature to temperature, they used just several variables at several pressure levels. We have seen here temperature, humidity, zonal and meridional wind at 700 and 850 hectopascals. They are trying to estimate the regional temperature. They use two different approaches: a perfect prog, which is trained in reanalysis like predictors of data, and the model output statistics trained with global climate models directly. And they used the saliency maps to show which variables and regions the model focus during the prediction. We have done this also in the hands-on training that I'm going to show you after the coffee break. So I will show you later some results on the Southeast Europe. Basically, they depicted a figure in which you can see the importance of each variable in the temperature prediction. And what did this say is that both the temperature, we can see that the wind variables have less importance than, well, these are two different locations. The location one near to an alpine region, and the location two, which is something somewhere up to Italy. And for both locations, they gathered information that the better predictions or the predictions that contributed more to the outcome of the model in that pixel were the temperature in both 700 and 850 levels. The meridional and the horizontal and the vertical components of the wind were the ones that were less attractive for the outcome of the prediction, giving less information to the model. And the humidity in the place of the location was also an important predictor for the outcome. And we can also have this one thing that we explained in the paper we published. We have a problem in the Pyrenean area, in the pre-Pyrenean area of Spain. And the worst thing is that all models perform worse than the bicubic interpolation. Then what's going on? We ask ourselves what's going on for all models obtaining worse results. All deep learning models are obtaining worse results than a simple approach as a bilinear or a bicubic interpolation. So something has to be going on. In this case, it's not with the model, it's with the data. We have seen a problem during our last couple of weeks. We have seen a problem in the Serra data because there is a big difference during the training period. The training period that we have taken is from 1980 to 2010, where there is a big bias between these two data sets in the points of of study, and then in the validation period and testing period, there is an abrupt change in the temperature of Terra that makes the model not be able to capture this, and this is why the bicubic interpolation in the 2019 and 2020 years, which are the 2019, 2020, and 2021, the ERA5 and Terra are so close that the bicubic interpolation is obtaining better results than the other 2 or 3 models, because the other models were trained in a period where the bias was really high, like there was a 3-degree or more bias. So we have discovered this in the input data, in the data of Terra, and we are going to add it to the next version of the paper. And I think this is all for now. It was till 11:15, right? So I think it's great. I don't know if you have any question.
There is nothing in the chat. Maybe if somebody has questions, just unmute and ask, or you can leave it for the discussion after the hands-on session. So
Can I ask something?
Yes, please.
Sorry, William. Antonio, thanks for presentation. Do you know what is the reason why there is such a big difference between these two data sets? So you showed the ERA5 and SERA data set. So I'm not sure, did you get me?
What was the question?
Do you know what's the reason behind the such a big difference in data sets?
No, we think that they have documented it in the eSIM.uf user forum, which is from where we are downloading the data. They have documented that there is a great difference in the climate change signal from ERA5 to Terra, and this is why we discovered this anomaly. In which the difference between ERA5 and Terra in that latitude longitude points was not stationary. I mean, it is time dependent, and this is why this abrupt change in the difference of the last years is not captured by the deep learning models. But we don't know really why.
Okay. Check further, I guess. Yeah.
There is another question in the chat. Do you want me to read it, or
I can, okay. I think. Are there any methods to interpret the structural complexity of different black boxes? Evaluate the group of nodes of deep learning networks and attribute the patterns to difference in performance. Evaluate the group of nodes of deep learning networks and attribute the patterns to difference in performance.
Antonio, can you hear me?
Yeah, because I don't really know what you are meaning here.
Yes. Perhaps it wasn't clear. Just because we now talked about visualizing the patterns that some algorithms see, but are there any methods like decision trees? When you look at the decision tree network, you know what's going on. Are there any methods to look at the structure of neural networks and just understand what's going on, what the different areas mean, and make a link with differences in performance?
Well, there are sensitivity analysis methods that are like the most simple to use, in which you try to include fake data inside the input data to see how it affects the performance of the model. I don't know if you imagine that we have in our problem of input data at low resolution, output data at high resolution. You can change some pixels from the input data to see how it affects the output. But I think that there is no way to, because these methods are gradient based, so you are calculating them by changing all the weights in the neural network. Well, you are studying how the weights in the neural network affect the output of the prediction. So in these methods, you can get which neurons or which layers are changed more with this sensitivity analysis.
Okay, thank you. Yes, thanks for the answer.
If there is no more questions, maybe we could take a break until 11:45 and then continue. Is that okay? Well, Daniel, just regarding the first question, both assimilate different data sources, including measures. So this is the answer for the first question, Dragan. Maybe you should just read the chat. Can you access the chat? It will be much easier than me to read it for you.
Yeah. Thanks.
Well,
So
it is
not an answer, but it is our idea.
Yeah. Okay. So well, it's an answer to a question. It's just your opinion. So okay, thanks, and see you back at 11:45. Okay.
Perfect. See you.